Section 2.4a, significant figures. No, not that kind of significant figure. If you're in math and you have the number 2, that's pretty straightforward. It's 2. It's exactly 2. And, math people, they always get it just pretty easy. However, it's not always like that. In science, we might be measuring something and we might say, well, it's 1.9999, or maybe it's 2.001, and we round both of those off to the number 2 instead of leaving it that way. And there's a difference there. For us, we're always measuring things, and every time that you're measuring, and any time that you round off, you're always going to have error. So every measurement we ever make will have an error. So let's talk about why that works, or how that works. And I've got my graduated cylinder, and I also want to kind of talk about how we should do this. And I put some food coloring in some water just to darken it up so you could kind of see it a little bit better against the white background here. But if you look at this, you can kind of see that here's my 80 mark, and each of these is 1, so 81, 82, and it might be a little difficult for you to see, but it's somewhere between 82 and 83. It's not quite to the 83 mark, not down at the 82 mark, so it's somewhere in between there. So anytime in chemistry that we want to make a measurement, like on this graduated cylinder, it's marked to the nearest whole number. We can always go one place farther. So, we always have to measure it to the nearest tenth. So if you told me that the answer that you got here was 83, that would be wrong. You didn't get as many significant digits as you could get. Instead, it should be 82 point, and then we're going to make a little estimate. And as I look at that, I would say it's probably 82.8. So that's our measurement that we want to go with, 82.8. Because I can measure this thing to the nearest tenth. Now, let's say that I take that same liquid and I'm going to put it in a different graduated cylinder. Got a great big one here. So if I put that liquid into this graduated cylinder, you can see that this graduated cylinder, each of these markings is by tens. So I'm measuring by tens. I can always estimate one place farther. So on this, I could maybe say, well, it's 82 or 83, and looking at it, to me, it looks like it's probably, I would say it's like 82 or something. And so with the other one, I got the 82.8 because it could measure a little bit farther. That makes that 8 a significant number in that reading, but in this one, the last number is the 2 or the 3. And let's say that we go with the 2. What this always means is that last digit is an estimate. So in my first number, the 82.8, my 8, the last 8, is an estimate. And there's some error there. It could be 82.7, could be 82.9. There's some error between those two. In this measurement, it's 82. And the last digit 2 is an error, or it has some error involved in it. It could be 81, it could be 83. So that's why in science, when you're making measurements, these things called significant figures are very important because they tell us how good our measurement is. Okay. All right, so here's the rules. Put these in your lab notebook. Okay, you will want these rules written down. Rule number 1, all non-zeros are significant. So that means the numbers 1 through 9, every single number in there is significant. So if I asked you how many significant digits are in the number 23, you could easily tell me there are 2 because there are 2 non-zero digits. Or if I said how many are in the number 349, you would say, oh, there's 3 because there's 3 non-zero digits. That rule is easy. One rule for the numbers 1 through 9. Every other rule concerns 0. 0 is the troublemaker. Rule number 2, all zeros between 2 non-zeros are significant. What do I mean? I mean a number like 104. Here's a 0 in between. Therefore, because it's between two non-zeros, it is already significant. So any number that's between two others that are significant is automatically. So I don't care how many I have. Let's say I have 2, 0, 0, 0, 9. Okay, all of these are significant because they come in between, somewhere in between a non-zero number, and therefore this has 5 significant digits. This one has 3 significant digits. Or the number 8, 0, 0, 0, 0, 0, 0, 2 has 1, 2, 3, 4, 5, 6, 7, 8 significant digits. Easy rule so far, okay? Rule number 3, all beginning zeros, or I call them preceding zeros, are not significant. So in the number like 0.0025, these zeros are not significant. They are what they call placeholders. They hold value, place value, and they're only there to let me know that I have a really, really small number. Like that. In this one, for instance, there are 2 significant digits. Think of it this way. If I were to write this in scientific notation, I would get rid of those zeros. And if that's the case, then they're not very significant. Okay? Or take a look at this one, 0.00604. How many are there in that one? Remember, preceding, ones at the beginning, those aren't. No, no, no. But this one is between 2 others, so yes, this one has 3 significant digits. Last rule, ending zeros are significant if the decimal point is written. But they're not significant if the decimal point isn't written, if it's just understood. So let's take the first one. Let's say that I write 40.0. Okay? If the decimal point is written, ending zeros are significant. Therefore, this one is significant because there's a decimal point, so it's significant. But if I write the number 40, no decimal point, this one is not significant. It's an ending zero, and it is there's no decimal point, so it's not significant. So this one has 3, this one has 1. Okay? Or let's say that I have the number 400, but you know what? It came out to be exactly 400, and I want to say, hey, I want all of those digits to be important because I measured it that accurately. Then I just put the decimal point. So if I see in science, there's a difference between this number, the 400 with a decimal point and the 400 without the decimal point. This one would have 3 significant digits. This one, only 1. I want you to stop the video now and look at these numbers, and I want you to tell me how many significant digits are in each one. Don't just wait and go on. You need to start thinking about this. This is a very hard thing to understand. So stop the video and tell me the answers. All right. This one, I just kind of did them in order if you followed through the rules. So the first one, 798, they're all non-zeros, so therefore there are 3 significant digits. On the second one, 906, the 0 in the middle is significant because it has significant digits on either side of it. Therefore, there are 3 in that one also. In the next one, preceding zeros, numbers in the front, they don't ever count. There's no time ever where they will count. And that would make this one also 3. Looking at the last one, or the next one, there is a decimal point. That means that zeros at the end, any of them, all of them, are significant. Therefore, there are 4 significant figures in that one. But on the next one, there's no decimal point. I didn't write it in there, okay? No decimal point. Therefore, there is only 2. Hopefully that makes sense to you. It's quiz time. Still have questions? Watch section 2.4a, additional help, for more information.